Good morning, everybody. I got an email about wanting to go over vector or integral setups, and there's something else. Why am I not remembering it? It was integral setup and Kirchhoff laws. So now on the exam, sorry, I can't zoom this one in. On the exam, I have put these exact topics like on the questions that they correspond to, right? So it'll be a little italics, sort of like 10-point font after the problem so you can see the topic. It does not reference the chapter that these things are. So just real quickly, because I know people are going to ask. Let's see, circuit reduction capacitors. What chapter was that? That was chapter 25. Potential was 24. Electrical power was 26. 27 and 27, right? So 3 out of 4 of the questions are coming from chapter 27 with that Kirchhoff rules times 2, right? All right, so integral setup. What do I mean by that? So you had an integral setup problem last time, and I think everybody missed it, some way, shape, or form. So that speaks to either how hard I made the problem or how shaky we are in integral setups. This time I made it multiple guess. So it'll look like a conceptual question, right? But I didn't list it as like you have an electric potential question that is conceptual, like completely conceptual, right? But your integral setup problem, I gave you 4 or 5 integrals to pick from. Does that make sense? So you can look at the situation and then you can look at it. But you do need to show me, like, explain to me why you are picking the one you're picking, right? Always has to have an explanation. So that can be just set up the integral and get, if it's the same as one of the choices I have, great, you've shown me, right? Or explain to me like why others are wrong or something like that, right? So you got a few more choices, a little bit more orientation as to what's going on. But what are the common setups that we've got? We've got lines of charge, and you're either finding like here, like on axis or off axis. There's rings. We set up rings. We set up disks, I think. Ooh, where'd my disk go? Right? So I'm pretty sure, isn't that all we did? Pretty sure that's all we did for integral setups for the electric potential. Okay? So outside of those things, you're not going to have to worry about it. And we have equations for the disk and the ring. The lines tend to throw people a little bit more for some reason. But when it comes to setting up integrals for finding the electric potential, and that's potential there, it's not volume, right? Your dV is K dQ over R, which comes from the electric potential of a point charge, right? There's no vectors in it, but you still need to find R, the distance. And in an integral, right? So the dq is going to be equal to lambda d whatever, dx in this case, right? Because you've got to teach the integral to go physically along the line of charge, whether it's an x or y. So again, that implies that there has been a choice as to some arbitrary slice or point on this line of charge. And the r is always the distance from that piece to the point where you're trying to find what you're solving for, right? So for this green R right here, where is this piece located? It's located at x, right? Some variable, it's going to change throughout the integration, right, as the integral sweeps along. It's a distance x away from the origin, right? So if we have a distance L between point P and the origin, what is R? It's L minus x. And that's, over and over again, that's what threw people off in setting up the integral last time, right? Not defining that distance correctly. Strictly an R vector, but we can just think of it as distances, right? If we were over here, we were going like, say, this distance right here, well, what I would do there is I would just write an R vector, right? Negative x I hat plus y j hat, right? And then what's the length of that? Right? For me, it's easier to define an R vector and then find its length than it is to try to remember several different ways of doing the same thing. So with this integral setup, right, I put the dq in, I put my R in, and I put all that in my integral. And I'm going to go from wherever it starts to wherever it ends. K lambda dx all over L minus x. Be careful with your units. Like lambda, make sure it's, length, charge per length. A lot of people forget to, they just throw the total charge in for lambda. But lambda is not charge, it's charge per length. Yeah, that's integral setup. We've done a lot of those before. Focus on getting the right R vector, you'll be all right. And these we have equations for. We developed them in class already. All right. And then Kirchhoff's laws. So maybe the best way to do this one is for me to just throw some circuits down and have you write out the equations. So let's do battery, resistor, resistor, we'll do that, and then we'll do battery and resistor. There we go. Why not? V1, V2, R1, R2, R3, so that we are all speaking the same language and can practice the same way. I'm going to make current 1 go this way, current 2 go this way, and current 3 go this way. I don't know. Does it matter if I get the directions correct? No. What matters? That I stay consistent, right? That if I pick this and I make sure I apply my conventions correctly, right? So now I need some loops. Loop number 1 will go that way. Loop number 2 also go clockwise. And why not loop number 3 clockwise around the outside? You tell me, you can do it on your paper right now if you want, but you tell me, starting at battery number 1 for loop number 1, what do I write? So 0 equals positive V1. Why is it positive V1? Our loop is going through the battery in what I think of as the forward or correct direction. Small plate to big plate. Okay, so positive V1. Next. Plus I3 R2. Okay, what happened there? We were going around like this, right? What direction is our loop direction? Down. What direction is our current direction? Up. So what does that mean? plus. And I got the plus right there, and then it's the voltage in that portion, right? And a voltage through a resistor is its current times its resistance. Okay? And then what do we end with? Minus I1 R1. Again, minus Y. So we came around this way. Which way was the current? That way. So they were in the same direction, meaning that it became negative. Some of you seem to be confused about like where current I1 exists. I1 is all of this section. It exists everywhere in that wire. Okay? It's born at this junction, flows along through all these series connections, back, and then dies here, turns into something else. Okay? I3, where does I3 exist? Only in the middle, right? It can only exist between the two junctions that mark off the segmentation. And then where does I2 exist? This entire outer loop right here, right? Outer loop, the outer U-shape section. This is where I2 is, right? And so because we said it's going clockwise, that means at the top it's going to the right, on the right it's going down, and on the bottom it's going to the left. It has to have that direction of flow, right? Which is why I tend to refer to it as clockwise or counterclockwise, so that way it doesn't matter where I am on the schematic, right? If I'm on the top, bottom, left, right, I keep a consistent direction. All right, loop number 2. 0 equals, start at V2. Positive V2. So here's something you might want to try. Just another method for you. Rather than doing the sign and the voltage at the same time, write down all the voltages first and then go back and do the signs. So what do I mean by that? Starting at V2, I'm going to have V2, and I'm going to leave a space in front and behind it. And then I'm going to have I2R3. That was awkward. And then I'm going to have I3R2. And then I get back to V, right? I'm just sort of tracing out. I pass through the battery, got it. I1, R3, got it. Come around here, okay, now I'm R2, R3, right? Like, see how I didn't worry about the directions at first? I just wrote down the 3 voltages I'm going to have in that loop. And now I can go back and do the positives and negatives, right? So as I move through V2, positive or negative? And then I2, R3? And then I3, R2? Okay, so you can break it up like that if you want. If you're having trouble, holding all of the things in your head about what I'm supposed to write down. Write down the voltages first, leave little spaces, go back through, get the directions. All right, and for kicks, let's do number 3. Starting at V2, sure. Minus I1, R1. And that gets us back to V2, doesn't it? So. Yeah, we can do the junction rules. So call that junction A, call that junction B. Junction A, that's not a loop, that's a junction. Yeah, so take a look. Like I1's coming around and going into A, isn't it? I3 is heading upwards into A. And what's I2 doing? Heading out. So I'm going to write this as I1 plus I2 equals, nope, I1 plus I3, because I messed up my symbols, equals I2. In equals out. Conservation of charge. And then for practice, let's do B. Here's I1. There's I3. There's I2, right? Which one's going in? I2. And the other 2 are going out. Okay? So examination-wise, you can do a Kirchhoff's rules problem without ever having to do any math. Think of it as a conceptual question if you want. But I can test you, like I can say, write down loop 2 for me. That could be the question. Or, here's a bunch of equations. Which one of them is correct? Which one of them is wrong? There's lots of different ways to like ask the question, but it's the same idea, same question, same concept.
Would you, so on a test, if you wanted us to find the current of something, would you give us one of the variables and then?
Yeah, so I don't think on this test I made you solve any of your Kirchhoff's law. Maybe I did. No. I don't remember what I did. I guarantee you that if you are being asked like to solve this problem, solve for I1, I2, I3, I'd probably give you like I2. And if I give you I2, this problem now becomes a 2 equation, 2 unknown problem. And I consider 2 equations with 2 unknowns to be definitely in your abilities. Some of you were like, differential equations, I got your back, Mr. Balogh. But algebra, haven't seen it in years, right? But 2 equations, 2 unknowns should be, I don't know, is it fair for me to expect you to be able to do 2 equations, 2 unknowns? I think so. No. Why do you expect any math, Mr. Balogh?
What is this about? I thought you hated math.
I do hate math. I used to teach physical science, which was, I called it physics for poets. All the English majors and stuff that had to get a science degree, science thing for their general education. I would pull out a division. Like Newton's second law. What's the force if the mass is something, right? What's the acceleration if the force and mass are known, right? They go to pieces, man. Go to pieces. They could write beautifully. No? You're in the right place, Lewis. I mean, beyond this, there's just like, you can just draw circuits and practice drawing your loops, right? I don't know. Why is it that you think you have to get it perfect the first time? Well, eventually you got to do it on a test, but I'm saying the first time you try something. Why do you have to get it perfect? Why do you? Yeah, it's somewhere along the K through 12 system where you either explicitly or taught through bias that it had to be perfect the first time? Yeah, well, we can talk about that, Liz. Yeah, yeah. Because your parents won't be mad at you if you get a B. Yeah, no, I get it, but like.
You only get one chance?
No. One opportunity. This is it. I always tell people, and some of you believe me, college is the best place for do-overs.
Oh, yeah,
It really is. College has got your back when it comes to do-overs. I know it doesn't feel like it sometimes, but yeah.
It's all good. It's my 4th time.
When you get to work, like a job, they don't give you very many do-overs. I know people that have been in jobs where one screw up and that's it. Hopefully you find a job where they let you make some mistakes. Just own up to it. Some of you are like, you have no idea, Mr. Bay, what you're talking about. You never left school. Fair. Absolutely fair. I worked in industry for just a little bit as a grad student. That's because I was done writing my thesis and didn't have anything better to do. So. All right, so that was that email question down. What are other questions? I didn't think I saw any other. Yeah, no, my email is just full of register now for Lenovo Education. Electrical power. What? Yes.
Where do we know where to start comparing and go to? We just base off of one of the
Where do we know to start the current? The current can only exist in a branch of the circuit. And there are 3 branches because my junctions have 3 wires coming out of them.
Are you assigning the directions arbitrarily, or are you just...
You can.
Okay.
I think on the test I gave you directions just to make sure I could grade everybody's.
That's good.
I'm not sure I understand your question.
So, like, the example we did in class
Yeah.
last time, I was trying to, like, see your thought process on which way to make the curve.
I just guessed.
It's arbitrary.
Total arbitrary, yeah.
Okay.
In this example right here on the screen, what I do is I just follow the batteries,
Yeah, that's what I was...
right? I just assume a current is going to follow a battery. It may not. I might end up with a negative sign somewhere, but I don't care, right?
Are you fine with us just being like, I did the direction wrong?
Yeah. Yeah. But if I give you current directions, use those. Because otherwise I'm going to grade it wrong. Because I'm expecting maybe a certain thing, right? Like, I'm not sure that that's very clear. If you are just given a circuit and there's no currents and no loops specified, you are free to pick whatever you want, right? But I think on the exam, I gave you a circuit and told you what the loops and current directions were so that I can make it easier for me to grade. And it was one less thing that you guys had to worry about choosing, right? You just had to apply your Kirchhoff's rules. Somebody asked about power. Yeah. What's your question about?
I have a question
On this?
test. How many currents would we get on a Kirchhoff's rules problem?
60 or 70? No. You never went over 3 on your homework, right? So 3, 2, not 1, because that wouldn't be Kirchhoff's laws. My 4A students are taking their Newton's laws and energy test the hour before you guys are taking your test this coming Thursday, right? So they're freaking out about all that stuff, and they were like, Mr. Balogh, can you give us more practice? And I was like, sure. And so we just went to the end of the book and end of the chapter, and I started pointing out ones for them to do. And I said, what would happen if I gave you 30 homework problems every week? And they freaked. They're like, no, Mr. Balogh, you can't do that. I was like, I can, but I won't. Yeah.
6, 8 hours.
Well, I mean 4. Compared to this.
But the sad part is that the 10 that I give you, the 10 actual problems, then I give you some conceptual ones, that represents like a minimum number to try. Good morning, Lewis. Electrical power in watts, current times voltage. Also, current squared times resistance, or voltage squared over resistance, because of Ohm's law, right? So units are watts, and a watt is a joule per second. So be able to calculate the power, maybe be able to calculate the cost, right? If you're given, we did in class, like it was 14 cents per kilowatt hour or something like that, right? Can you find out how much it costs to run it? Or how much energy does it take to run a light bulb for an hour? Well, once you find the power, how do you find the energy? Power is work or energy per time, right? So the energy will just be the power times the time. And if you're running it for an hour, how many seconds is that? 3,600 seconds, right? So I'm hoping, letting you see behind the curtain and how the sausage is made and all those idioms. I'm hoping the power one is a quick, easy problem for you to just do and move on. I believe in you, Lewis. So, the power one is meant to be confidence boosting.
It reminded me, but one of the homework questions is like find the resistance in a battery.
Yeah,
Is that any different than just finding the resistance of?
Ohm's law. V equals IR. Yeah, it's no different. Is that just generalized murmuring about your existential dread, or do you have questions? Circuit reduction? Capacitors or resistors? Both?
Would there be any difference to doing both? Like, would you have to? And this doesn't.
In the same,
Yeah, like if you had a resistance.
yeah, then it's called an RC circuit. We didn't do that. Requires differential equations.
It was so scary. Yeah, why did you do that? And the hint was like, you could do this. No, you can't. I cannot.
You can find a resistance. It's a conceptual one that doesn't work in reality. Okay.
All right. Find everything about everything.
Is that middle one R1 or R2?
The three on the left are R1s. And then these are R2s. Do you? I have no idea. I'm making it up as I go. All right. So what do we do first? Reduce, right? Go as far away from the battery as possible. So battery's right there. So I'm going to try and get over here, right? Are there any, like, what can I do with any of these things over here? Which ones? Good. Okay. I'm going to regret this. All right. Can I do two at the same step?
Yeah, those are also series.
Because those are series, aren't they?
Yeah, and then
You get that wrong when you do. Okay.
and now it's all in parallel.
So we'll do it. Oops.
Get it done with.
So let's see, what am I left with? I'm left with that. And then I'm left, and I can draw this one over here. Okay. So this is 2R2, isn't it? Because these went together in series. I'm gonna hate my life for doing this all symbols. All right. And then this is an R2 right there. Okay. Can I now combine? What can I combine now?
Series on the left.
So, well, not that, let's continue working as far away from the battery as possible.
Parallel.
So those are in parallel. How do you tell? Junctions, right? Junction right there, right there. All right, so this is a parallel combination. It's 1 over R2 plus 1 over 2R2. Inverted, right? Oh, golly. That's 2/3 R2. I think.
Yeah.
Okay. So what have I got now? I have that, and that. And this is 2/3 R2. All right. Now what?
We can combine the R1s and series.
I got series R1s right here, don't I? How do you tell they're in series? There's no junction between them. There's a corner, but there's no junction. So I can combine those in series. Let's see, using red for series. So that's 2R1. And I now have a drawing that looks like this. Now, notice I did a funny. What did I do? I moved it. Am I allowed to move it? Yes, as long as I don't change how it's connected. So the movement of this resistor up to this wire fundamentally does not alter the fact that it's still connected in parallel with this one. Why would I redraw it like that? To make it easier for me to see that they're in parallel, right? Because this is in parallel with both of these simultaneously. So I just decided to redraw it and maintain my schematic diagram connections. Okay, so now what do? These are in parallel. So let's see, that's going to be 2/3 R1, isn't it? Because it's the same math as the R2's one, right? It's 1/2 R1 plus 1/R1 inverted becomes that. All right, what have I got now? I have a battery. And I have a resistor and another resistor. And this one's 2/3 R1 and this one's 2/3 R2. And what are those? Series. So I've got a battery with one resistor in it that is 2/3 R1 plus 2/3 R2.
I'm sorry. I'm afraid I can't do that.
Yeah, I wouldn't do that either. I would not do that either. It was good timing. All right, so there's the reduction, right, for resistors. We follow similar rules for capacitors. It's just with capacitors, you switch the rules, right? When they're in series, it's the inverse adding. And when they're in parallel, it's this adding.
Is that 2/3 R2?
Yeah. It's very messy handwriting is what it is. So now that I know that, if I had numbers, I would know what that resistance is. I know what the voltage is. What can I find? I can find the current coming out of the battery. And then I start working my way backwards, applying Ohm's law to every simplification step that I made, right? If I know the current in this equivalent resistor right here, then what do I know about these two that were in series that made it up? Same current. Why is it the same current? Current's the same in series, right? It's the rule, right? Now that I know the currents in those, and I know their resistances, I can find the voltage. So I find the voltage in this. Well, where did the 2/3 R2 come from? It was right here, wasn't it? We can do this one, right? So 2/3 R1 came from this pair. What's the same in parallel? The voltage. Well, we found the voltage over here, right? So we know the voltage in these two, right? And if we know the voltage and current right there, we can find the, if we know the voltage and resistance, we can find the current. And then if we know the current, it's the same in both of those because they're in series, right? It's an unfolding, applying the what's, the same using Ohm's law the entire way, which is a exercise in keeping track of things, right? And doing little tiny calculations along the way and doing math that would make English majors sweat because it's division. Circuit reduction. What was it? I wrote them down. It's funny. Circuit reduction capacitors and resistor circuit analysis. So circuit reduction capacitors, this is from the topics. That means you're just reducing down to an equivalent capacitance. What's the equivalent capacitance of this whole circuit? Done, right? The resistor circuit analysis, you're doing that with resistors, but you also are being asked to go back and find like what's the current in one or power or whatever in one of these things, right? So the resistor circuit analysis will require the unpacking. The circuit reduction capacitors is just show me that you know how to add capacitors in series and parallel.
How the hell do they do this when they make CPUs? Oh my god.
That's what the AIs are for now, right?
Before AI.
CPUs are a transistor is a little bit of a different type of connection. So there are circuits in there, but they're not circuits like these. What I want to know really is not the CPU. CPU seems easy to me. It's very complicated. It's got lots of transistors in it, but like there's sections of a CPU that make sense to me. What doesn't make sense to me are motherboards.
Oh yeah, no. I'm lost. Every time I look at the traces on it.
How do you integrate all of these different systems that are all talking at different speeds with a different set of voltages and a different set of rules? Motherboard manufacturers be praised. Like it's just amazing. Yeah. So. And GPUs are just throw lots of transistors on them and see what happens. And then apparently forget to put some transistors on them. You guys hear about that? NVIDIA had a failure of some of their compute units on their chips. They didn't know it till they released it. I guarantee you they knew it. Guarantee you they knew it. Yes.
Can you go over one of the power ones from the homework?
Sure. What power one from the homework? You have no idea. They're all tricky. It's physics, right? Let's see. That would be chapter 26, wouldn't it?
Can we stay in this class for like 3 hours today?
I mean, you can. I'm going to leave.
Cry on the ground.
Here's a power one. 120 watt light bulb, 120 volts. How much does it cost in dollars for 31 day to leave it on continuously? Oh my gosh. Continuously. Well, just go look at my neighbor's house. Their outdoor lights are on 24 hours a day.
You don't ever go to them like, I'm a physicist, you know?
Oh yeah, I've talked to them. They don't care. Actually, they walk away as soon as I say, hi, I'm a physicist. No. I get along really well with my neighbors. I just don't understand why they leave their lights on. All right. So what was I doing? Oh. I disagree with my neighbors a lot, but I get along really well with them. Wait, you are a fun neighbor or you would be a fun neighbor? Yeah, you live in the middle of nowhere?
Like my neighbors all speak Spanish, so I
Oh, you can't communicate with them.
want to have fun, but it's mostly Spanish 24 hours.
Yeah. I hear that. Okay, so how much does it cost? Well, we know it costs 6 cents per kilowatt hour, so how do we figure out what the kilowatt hours are of this light bulb? So we need to get the 120 watts converted into kilowatt. This is chapter 1 problems, really, okay? How do I take 120 watts and put it into kilowatts? What does kilo mean?
1,000.
Means 1/1000, right? Okay, 1,000 watts, right? So I got to divide by 1,000. So this is 0.120 kilowatts. All right. How many hours is this light bulb on? 31 days. In one day, there are 24 hours, right? So what's 31 times 24?
So 740.
Isn't GoodNote supposed to do this math now?
740 hours. At least I think.
It's not doing it. I thought GoodNote's updated so it could do math. I did an equal sign.
44. Damn.
31 times, do I have to write it like this?
Get that in your head, bro.
Just did
It's just not detecting it.
goodness.
Big circle.
I'm getting, did anybody get it? 744? Okay, so there's the number of hours. How do I find kilowatt hours? Don't divide. A kilowatt hour is not a kilowatt per hour, it's a kilowatt times an hour, right? So I multiply by 744 hours. And what's that? 744 times
89 and 0.28.
89.3 kilowatt hours. All right, it costs 6 cents per kilowatt hour.
So times.
89.3 times 0.06.
5.36.
Which is the answer, 5.36. How'd I do, Rose? Did I answer a question? Was that sufficient? Was I going too fast?
Those ones were easy, but there weren't other ones on there with like the resistance and the current that was like kind of blurry out.
Would that be like the one that's on the test? Okay.
This one.
This one?
Yes.
Kilowatt heater element from a dryer has a length. Oh, that's okay. That's okay. So they're just asking you to remember the resistance formula for this one. So the key connection here is that resistance is equal to resistivity times length over area. Yeah, it's a row. And power is equal to current times voltage. But it's also equal to current squared times resistance, or voltage squared divided by resistance, right? So if we're removing that 12 centimeters, we're altering this length right here in this equation, right? So maybe I'd use that. I guess since they give me the voltage, I guess I'll use V squared over R, right? So I would find the resistance, since I know the power. I'm not going to do this whole problem. And I know the voltage, I can find the resistance. And then once I know that resistance, maybe I should do it. Once I know this resistance, right, and I know this length, I can solve for what this is. That's going to stay the same for the new one. but we're just going to take this and make it 10 centimeters, which then gets me a new resistance, which then I put back over here to find the new power. Too fast? Okay, that's the and I'm not getting that detailed on the power one for you guys.
So you're saying you found
All right, okay. So does somebody have a calculator? I just didn't want to do calculations. 1400 equals 120 squared over r. Oh. You know what? But I was going to do it all symbolically because I just figured out a way to do it that way. Do you guys want all the numbers instead? Numbers or symbols? Symbols? Okay. Power 1. Voltage is not changing anywhere here. So my original resistance is going to be equal to the voltage squared divided by my original power, call it power naught. This original resistance is equal to rho L naught over A equals V squared over power naught. Okay, so my rho over A is equal to what? It's equal to V squared all over L naught P naught, right? So my original voltage, my original length, and my original power is what this rho over A constant is. I don't know what the cross-sectional area is. I don't know what the resistivity of this dryer element is. But I do know that the ratio, rho over A, is equal to whatever that number happens to be. Okay? Well, that's true for my new section resistance, right? My new section resistance is going to be rho over A times my new length, right? Which I'm given. I know what that is, right? So my new resistance is going to be V squared over the original length, original power, times my new length. And then my power is equal to V squared over R. And so this is V squared, and again, the V's are the same, right? The V's never changed. All over my new R. My new R is V squared all over original length, power length, times L. So something now cancels. My V squareds cancel. Right there. My color back. L naught, power naught, and L are left behind. So now my new power, okay, should be L naught 0.10 times power 1.4 kilowatts all over my original length 0.12. So it's whatever that number is. What's 0.1 divided by 0.12 times 1.4? 1.17. So I made a mistake somewhere. What did I do? Did I type it in wrong?
It's 2.5 centimeters, not just 2.
Oh, 2.5 centimeters, not 2. 2.5 would be 0.095, right? 12 minus 2, yeah. No, that makes it even smaller. L naughts on top. Jeez. I even did it in symbol so I wouldn't get confused. 0.12. I was like, it's going down. It shouldn't go down. It should go up. 0.095. There we go. 0.12. It's just numbers. I don't like numbers. Because I had the right answer before I put the numbers in. 1 point. It's that number right there. kilowatts. Yeah.
Can we go over potential to energy using because there's that one with
Potential to energy.
the one with the partial derivative.
Oh, getting electric field from electric potential?
Yeah, that's what I meant to say.
It's not on the exam.
I don't know.
Yeah, I would have said something about getting electric field from electric potential. It's not it. Very few of you, I'm a little bit sad that very few of you didn't rake me over the coals for, where is it? Yeah, was that the last one?
Oh, no, we did. We just not to your face.
I don't even think I got that far. Oh, what the? I figured it out. Looks like
You got that one?
it looks like a Patrick doll.
Actually, yes.
I really
That's exactly what I did.
It's like a quilt. No, I figured it out.
I just looked it up.
Number 8 was worse?
Yes. Yeah, number eight was way worse.
I'm glad I stopped before number 8.
That.
What the hell is that thing? Yeah, Wheatstone joint.
Number 8. I had trouble with number 10.
Oh, you just draw the junctions. That was easy.
I think, is it now time for me to leave the room?
Nah, I figured it out for you. So cool.
So the trick with this one is to realize that there is a path through the maze that will take you only through batteries. So this one I saw and I was like, oh my gosh, I have to give this and they're going to hate me for it. So let's see. I'll show you the path through the maze.
Will something like that be on the exam?
Yeah. Bigger.
Extra credit question?
No. Although you guys never got, so the internet ruined one thing, and that's a problem called the resistor cube. I'll show you the resistor cube. Let me get this on here. Yeah. No, the resistor cube was what it sounds like.
For the oohs.
So there's resistors on every edge of a cube. Connect a battery from the lower left corner to the upper right corner. Find the equivalent resistance. It's not 0. It does turn out to be something fairly simple, and I don't remember what it was, but yeah. Getting the series parallel connection, you can flatten this cube out into a flat schematic diagram and work it out that way, but yeah. That's a fun problem. And by fun, I mean I didn't like it when I had it either. All right, so we are trying to find the current right there in this resistor, right? It's unavoidable to have to combine these 3 resistors together. But they're all the same, aren't they? Thing is, doesn't it say all resistances are the same? So R, 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 and R, right? So this is going to be, 1 over R plus 1 over R, which is 2 over, so that's R over 2. That's the parallel combination. And then I'm adding on 2 more R's in series. So what is that? That's 2.5 R, isn't it? Okay. I'm not sure that that's what mental calculation means. Maybe it does. I have to write it down. I can't do that in my brain, right? So what that means is all of these resistors are just 2.5 R, right? So now we've kind of collapsed that down, and I'm going to use my highlighter of joy to take you through. So now, starting here, I'm going to trace a circuit path, a loop, a Kirchhoff's loop, that will only take me through batteries and get me back to that point. Because if I go through any other resistors, my life is over. I forgot. No, I didn't. Well, I don't have to go through all the batteries. Kirchhoff's rules say for a closed loop of the circuit, what must be true? Wherever you start and end, you add up to 0, right? So, what do I have? I have plus, 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 plus. How many pluses is that so far? 1, 2, 3, 4, 5. And then I've got a minus and a plus and a minus. Why are these minuses? I'm going against the batteries, and that's plus. So I had 5 pluses over there. So now I'm at 4 because of the minus, and I'm back up to 5, and then I'm down to 4, 3, 4. So that means 4 times my voltage minus my current times 2.5 R. That's my entire loop. Solve for current. I know 4, and I know 2.5, and I know my resistance, 7.4 ohms, right? Solve for the current. So that one was a particular, it's particularly mean of me to throw that at you because your initial response is no way. Just give up, right? Don't give up. There's always a way. It's a lot simpler sometimes than you think. What the heck is going on over here? Electrical engineers, you can go figure out the resistor cube and every single current in every single how many currents are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's at least 16. Some of those, I think some are doubled up, but there's at least 16 currents in this diagram. And there's a minimum of, there's a minimum of 24 loops, probably more. Probably a lot more.
So, like, what could this perhaps be a model of?
Don't care. All right. What else do we got? Other questions you may or may not have.
Can we just go over like high versus low potential, and then high and low potential energy?
What's
Of like a charge? Positive versus
high and low potential energy of a charge?
Yeah, like
The
just
conceptual.
the conceptual stuff about it. Like why does a negative charge go from low to high, high to low, or positive to high to low?
Okay, so if we have a negatively charged plate up here, and we have a positively charged plate down here, where's the high potential? And so that makes the low up here. Why? We just define high potential as where the positive charge is. Okay? Where a positive charge, if put in between the plates, right, would roll away from or fall away from or be pushed away from, right? Just like we define high gravitational potential energy to be on top of mountains. We say it's high up there just because we say it's high up there, right? It's a convention, right? It's a definition. All right, so those are the conventions and definitions, and I put a positive charge right in the middle. Which way will it go? It'll go towards the low potential. But what will a negative charge do? It'll go towards the high potential, right? The potential energy is equal to that's work, Q times V, right? So whatever voltage we have, if we have a positive charge, right? Like if I stick a positive charge right here, right? It's going to end up with positive potential energy, isn't it? Positive potential energy meaning that it can, as it goes to lower lower electric potentials, it goes to lower potential energies. But what happens if we have a negative charge? We put in a negative charge for this Q, right? And it kind of flips what's going on. The negative charge right here is going to have high potential energy, whereas the negative charge is going to have low potential energy at the high potential. And again, I'm not responsible for how the universe is put together, the fact that there's two different kinds of charge, right? And that the mobile ones, the electrons, that's Ben Franklin's fault.
You say that one more time.
No.
electric one.
What?
The electron thing.
Yeah, what about it?
So it's the same electrical, it's the same potential.
Yes.
The energies was different. with
Yes.
different signs.
Yeah.
So the
'Cause it's a negative
electron
charge.
is,
Has high potential energy right there.
So the potential.
Why does it have high potential energy right there? It wants to get away from there,
yeah.
right? Why do my keys have high potential energy right now?
It's just the signs are screwing me up. I understand that, but connecting that, it's just the signs.
Yeah,
The slip in it is.
Ben Franklin.
That in gravity.
Ben Franklin.
So the potentials are defined, the energy is based on positive and negative.
Yes, the energy is dependent on the sign of the charge. A proton is 1,000 times more massive than a positron. A positron is an electron that's positively charged.
Oh, so it's the antimatter of the electron.
Yes. An electron that has a positive charge, so the mass of an electron, but the opposite sign of the charge. So it's an electron except for its sign of charge. It's called a positron. It's an anti-electron, but we just call it a positron. Physics 4C.
Who was the guy that found it? Who predicted it? Was it Dyson?
Positrons?
It was direct, right?
No. You're thinking of the neutrino, I think. Were positrons found by the Curies, maybe? No, they found alpha, beta, gamma. I don't remember who did the positron.
I think they found it experimentally with the
Maybe. Positrons are what's coming out of bananas. Bananas emit positrons. Yes. Inside or outside of you, they're emitting positrons. We're getting off topic here.
Can you show us a problem with 2 currents instead of 3? Most of the ones we did, they have 3 currents, but they have like 1 down the middle. But what one look like with just 2?
I don't know.
I don't think that can.
Yeah, you're going to have minimum of 3.
So we have to have 3.
Because anything less, it'd just be in series. And it'd be the same current. So it's 1 or 3, yeah. What I can do is I can give you one of the 3 to make the math easier.
Okay.
Does that make sense? That's, Can't think of anything? All right. What? Can we do what 4A did?
Do like you recommend us
Recommend homework problems?
Throw the book at throw it on my head so I don't know the knowledge.
Can you imagine if that's how we actually like had to write the notes down? Just it's just like, okay, so you know what? Oh.
All right. Modules, chapter, let's go chapter 27. And I just pick any one of these. It doesn't matter. I just need the table of contents. Chapter 27. Problems. All right. Chapter 27, problems. Ooh. Starting up here. Oh, well. What does SSM mean? Super sexy math. It means Student Solutions Manual. Oh, you've been in physics how long? You know? Okay. So that means, and where can you get the Student Solutions Manual? Look. I provided a link for it right there in Canvas. Ooh. So anything that says SSM on it, you can try it and see how they did it, and you'll have immediate feedback. Beyond that, the odd numbered problems. See how they have a little hyperlink underneath them? Click on that, it'll take you to the answer, just a numerical answer. Okay. No, it doesn't show you the work. Only if it says SSM does it show you the work. Okay. So you can just look at the pictures. None of those are good. I don't know what's going on there. That looks scary. You did a similar one. Here's a circuit. You could, immediately, is it Kirchhoff's or reduction? How do you know? Multiple batteries, right? How many currents in this circuit? There's 1, 2, 3, 4. So you could practice identifying the number of currents in these circuit diagrams. There's a segment here. There's a segment there. There's a segment there. Oh no. No, there are 3. Never mind. There's 3. Not 4. Yeah, I counted B as a junction. It's not. It was labeled, so I assumed it was a junction. How would you find the equivalent resistance here? Parallel and then series. That's scary. No idea what's doing there. So, yeah, I don't care what's going on in this part, but just practice reducing this circuit, right? Parallel series. You did that one. Kirchhoff's laws. So, like I said, I'm not even reading, I don't even care what the question's asking me. I just want practice in identifying things, right? This has got 2 batteries in it, so Kirchhoff's or reduction? It's Kirchhoff's. So what have I got here? I've got 1, 2, 3 currents. Kirchhoff's law or reduction? That's pure reduction, right? What do you do with these 2? And then parallel, and then series, and then parallel, and that's it, right? It's like series, parallel, series, parallel, series, parallel. There's the terror one that you had.
How do you do that one though?
You draw loops. You do it Kirchhoffs.
Yeah, but it says it's not, it's neither series nor parallel, right?
Right. That's why you can't reduce it. You have to use Kirchhoffs.
You have to combine them down.
No, you don't combine anything. You just draw a loop right there, and then a squiggly loop through it.
Okay, so you have to do it like that.
I gave you that one, right?
Yeah, that one was cool. That one was good. I like that.
So, and did I give you this one?
Oh,
But
yeah.
yeah, I think I did.
I think that was pretty good.
So there's lots of things here for practice. Those are RC circuits. Don't do those. Oh, capacitance. This one you already did. Woo! So how would you, like, where would you start on this one? So like, these are in parallel with each other. These are in parallel with each other. And then the combination would be in series, right? And then these are in parallel, should be in series with this one. And then whatever's on this side is in parallel with whatever ended up on that side.
You just go right past it.
Oh, it's computer specs, man.
What?
Can you go back up to the one you were just talking about? Not that one. Keep going. Keep going. That one. Wouldn't R1 and R3 be in parallel because there's a junction between them?
R1 and R3?
Yeah.
No. This wire right here, when I put these together in parallel, R1 and R2, this wire and this wire disappear. It's like a single resistor. And the same thing's going to happen right here. Those together in parallel will then be in series with the top. Yeah. The order of operations is to collapse like wires that have nothing in it. Try to get rid of those first. Kirchhoffs or reduction? Reduction first. I would reduce this right here. And then I'd have a series with those three and reduce those down and then do Kirchhoffs. So like I would simplify this part of the circuit and then do Kirchhoffs. Oh, it's a resistor cube.
Hold on, does that say brain resistance?
No, brain resistances down here. Circuit cube up here.
Well, the circuit cube's definitely a brain resistance.
What is going on? Leaping electric eel. Boy, I didn't go far. Well, these must be new. I don't remember this. Why is it what? It's biology. Don't ask questions.
Yeah.
It's not in his bathtub. That's just a tank.
Don't ask a man about his bathtub eel. You tell me you don't got a fish in your bathtub?
All right. I will see you on Thursday.